Okay, guys, I promised you that I would create some videos talking about our projects. So created the design for project 3 using the organization that I thought would have been best to have advocated from the beginning. Uh, so I'm going to go through and show you my design, show you the approach that I like. I'll have a second video on project 4, and then I'll have another video on project 5. So the first is project 3, which was the simple debounce, pause edge detect, running to a counter, and then going to our 7-segment display. So the top level module is fairly straightforward. The only thing we needed is the clock, the reset, our input, which in this case is a button, and then our outputs are our anode and our cathode, because we're going to be pressing the button, causing us to debounce the signal coming from the momentary button. Then we generate a 1 clock wide signal that will go to a counter. Then the output of the counter, a 32-bit counter, we drive our 7-segment display with so we can see the count. So the first thing I should have really stressed is that we should be creating the debounce PED as a separate module. So in that case, what we would have done when we go to use it is that we would have instantiated the debounce PED into our project 3. And here again, the port list, we have the clock in, the reset in. We need our tick, which is our 1 millisecond pulse that we use to sample the signal button, that we then eventually generate the PED, which will be used as the increment to our counter. So intimately associated with the debounce PED is the generation of the 1 millisecond pulse. And of course, here is where we had to do the mathematics, where we had to determine that the frequency of the clock to our board is 100 megahertz. So therefore, the period of our clock is 10 nanoseconds. And we had to figure out then how many of those clocks do we need to count in order to have a 1 millisecond elapsed time. So it ends up we need 100,000 count. 2 to the 16th is 64K, so 2 to the 17th is 128K. So we need 17 bits for our counter. So in the style I've chosen to design the 1 millisecond counter is that I have my synchronous block that at reset gets 17 bits of 0, else it will always get next count. Then how do we generate next count? That's the combinational block, where if we have fired off our 1 millisecond pulse, we want to start all over again, start the count all over again. Else, on every clock, we take the contents of our register and we add 1. This is always a very important construct, a way to build these structures. It's the synchronous element is what we're adding 1 to. The whole purpose of having flip-flops is to allow us to hold the state. The NT count is the combinational logic, so the input to the combinational logic will be the sequential logic output, always with a +1. That allows us to do our incrementing of our counter. So that gives us the counter, and it runs until we reach our terminal count, at which point in time our tick fires to the debounce circuit, and we could also then start all over again. So that's the instantiation of the debounce. Now let's go down and look at the design of the debounce itself. So the design of the debounce itself had 2 parts. I call the module Debounce PED. It's really, I think, a nice design to have as a standalone module in your repertoire. It allows you to just instantiate this. You then have to include the Debounce PED file in your project. And again, it's a synchronous implementation. We now have the tick that tells us when our 1 millisecond is up. We have the button, which is the input that we want to debounce. And then we have the PED, which is the positive edge detect. That means we have detected a stable debounce signal. And so we need a couple structures to allow us to do that. First, we need a 10-bit register, and I call it the shift register. And again, I'm using the same style where I have the shift register and the next shift register. Then I have a signal dB, which will be the output. We'll see that once all 10 bits of my shift register are 1, then we assert the signal debounce. Then for my pause edge detect, we need 2 flops, and I use the same style here. I have the flip-flops and the combinational logic to drive the flip-flops. So when we come down, and the final is the PED signal itself, which is the output of this block. So the first is our shift register. So one way to start is to look at the combinational logic first. And what we're doing is sampling the input every 1 millisecond. So when the input signal telling us to sample is a 1, we then grab the contents of the button and add it to our shift register. So it shows up in the LSB. We take what was the 9 LSBs, move them over 1, and then we can assign that to our shift register. When tick is not a 1, we have to hold the contents of our shift register intact. So the whole point of this is that it will allow us every 1 millisecond to take a peek at the button. If the button is 1 for 10 consecutive peaks, what will happen then is that our shift register will be filled with 1s and the output of our debounce will be a 1. Now that's the debounce circuit, but we've called this debounce PED. So now what happens here is we have to take the PED signal, or the debounce signal, and we have to make it available. In this case, I'm making it available to the MSB of this register. And then I'm moving the MSB to the right. So what will happen is that when debounce goes to 1, PD sub Q1 will go high. And then there'll be a situation on the next clock where it will go to the second bit as well. So we're looking for the situation where PEDQ sub 1 is high, PEDQ sub 0 is low. That is our debounce. Now that signal we take back to our design. So after the debounce PED, what we needed to do was to implement our counter. And this is a fairly simple circuit. It follows the same approach where you have the counter and the next counter. And our design is whenever the PED is a 1, we want the contents of the counter to be incremented by 1. So then we assign that value to the next counter. When the PED is not a 1 or it's a 0, we just maintain the contents of our counter. So that gives us the combinational front end to the counter itself. And then the synchronous portion, which is very simple. Always at reset, we clear the contents. Else, we take the contents of the next counter and load it into the counter. So that takes care of our counter. Now, what we have to do after that is we have to be able to then see or observe the results of our design. So we need to take the contents of the counter and make it available. So I used my previous design that I had data as my 32 inputs. So now really I'm just taking the 32 bits of the counter and bringing it into my design that will feed my 7-segment display. And we know that we have to sequence through the 8 LEDs, 7-segment LEDs. So we need a counter, a count. We'll see it down here. It's going to count from 0 to 7. That will allow us to select which portion of our data is being made available to our 7-segment display. 0 gets the LSBs, 7 gets the MSBs. So that is our mux to bring the data in. Then as the data comes in, we need to do a transformation. We need to transform those 4 bits into the 8 bits that will drive the cathode to be able to display the value that we are interested in. So always at the combinational inputs, we are looking at the output of the previous block and we are generating the cathode signals. That's of course a 0 to 1 to 2 to 3 all the way down to E and then finally F. Now we have our cathode signals going out. The last thing we need is we need the anode signal. And again, it's a synchronous shift register. In reality, it's a rotate register. And what we're doing is we're rotating zeros through our anode register. So we start off by initializing it to FE, and whenever we are going to rotate it, we then, the next anode moves the 7 LSBs over 1, and we bring the MSB back around. That allows us then to continuously recycle that 0 through the anode rotate register. And then at the same time, each instance where we are incrementing our anode counter, we of course are shifting our anode register. We of course are incrementing the counter that is driving the 7-segment display select. The count here, which is choosing which of these values appear. So I hope this helps. It's a walkthrough of the design. I'll follow this up with a simple little one that gives the test fixture for project 3. Okay guys, what I wanted to do now is I wanted to give you a walkthrough of the test fixture for project 3. It's pretty straightforward. Again, we've discussed that the inputs to our project are the clock, the reset, and the button, which is the momentary button that we press. The outputs are the anode and the cathode. So we are pushing a button and we want to see the 7-segment display reflected. So I have to instantiate my project into my test bench. I use the explicit mapping where each of the ports of project 3 are called out with a dot, and then each of the signals from my test bench that I want to interface to my design go in the parentheses. So in this case, I've named everything the same, so it looks a little redundant, but always keep your perspective. These are somewhat like a record annotation in software. They show the ports of project 3 explicitly. The order doesn't matter. If you wanted to put one up above or below the other, you can do it. And it doesn't matter because we're telling it exactly what signal we're connecting to that port. The other technique is where you just type clock, comma, reset, comma, button. That's called implicit mapping or positional mapping. I don't encourage you to do that. I'm at a situation where at Northrop again, we have modules that have hundreds of ports and you can get really confused if you end up transposing them. So once I've instantiated my design, the next thing, of course, I always need to do is to generate my clock. So every 5 nanoseconds, my clock will toggle, and that will give me my 10 nanosecond period. Then it's a very simple sequence to walk through here. We start off, we initialize the clock to 0, we initialize our reset to be active. I like this approach because then you don't see the red at the start during the simulation. We have the button as being off. I'm going to use I as an iterative variable to allow me to cycle through several times. My choice of 100 here is arbitrary. I'm just letting it wait 100 before I turn reset off, and then I wait 100 again before I begin testing my design. Now what I want to do, I'm going to walk through, and you don't necessarily need to do this 16 times, but this is what I chose to do just so you could observe the counter when you run your simulation. And you could see the 7-segment display switching, but exactly what they represent is not intuitively obvious. But if you keep track of the counter while you are running the simulation, you'll be able to verify that your counter is definitely incrementing 0, 1, 2, 3, etc. So what I do in the iterative loop, I assert the button. Then I wait 15 milliseconds. Now, our debounce is supposed to debounce signals less than 10 milliseconds, or greater than 10 milliseconds. So you could have made this a little shorter. I chose 15 just so there's no ambiguity. So I wait 15 milliseconds, then I turn the button off. Now, just like asserting it, I need to hold the button stable again for 15 milliseconds to make sure my 0 gets through to my circuit. So I'll do this 16 times. Just one comment, when you run your simulation, if you take a look at the signal, you'll see the first count happens quicker relative to time 0. So that's because we only wait 15 milliseconds to assert it. But after the first assertion, we have to wait 15 to deassert it, then 15 again. So following the first assertion, or where your counter will increment, you'll then have a 30 millisecond period. So the waveform will show you 15 milliseconds, then 30, 30, 30, 30, 30. So it's a relatively straightforward, relatively simple test bench, but it allows you to debug your design. As you're running this, you can go in and look at the debounce shift register to make sure that you are filling it up with ones. You can then make sure after 10 consecutive ticks that your output dB goes active. Then you could follow that through your PED circuit to make sure you get your pulse out. Then you follow the output of that into the counter to make sure that the counter gets incremented. Then when you program the board, of course, you'll be able to verify that all of the path works from the button through to the anode and cathode signals. So I chose not to go through the simulation itself. I chose not to go through the actual implementation, but it gives you an overview of how I would approach this as far as the design, which was the previous video, and now how I would approach the verification. So hopefully this helps, and we'll see you guys